today is properties of multiplication and addition. All right? Now, let me put down that word property. P-R-O-P-E-R-T-I-E-S. All right? And as a matter of fact, there are other words that we use in mathematics that means about the same thing as the word properties. And what I'd like to do is to write down some of those words, and then we want to understand exactly what we mean by them, okay? Another word that we use is axioms. Axioms, A-X-I-O-M-S. And another word that we use is assumptions. A-S-S-U-M-P-T-I-O-N-S, assumptions. And as a matter of fact, there's another word that perhaps you're not too familiar with. The word is postulate, P-O-S-T-U-L-A-T-E-S. Okay? Now these four words can all be used interchangeably for something that we will accept as being true. Okay? Any statement, well, let's make it plural, statements which we accept, A-C-C-E-P-T. Notice I'll underline the word accept. I'll emphasize that, which we accept as true. Okay? As true. Statements which we shall accept as true. All right? We're not going to prove them. We're not going to try to reason them out in terms of a logical proof. But these are ideas which in mathematics we all agree and say, yes, of course, I know that that's true. All right? And that's what we want to look at today. And these are some of the properties of our real numbers that we are going to be concerned with. Okay? Now, as a matter of fact, one of the first set of properties that we should look at have to do with our relation of equality. Okay? Our relation of equality. Let's look at some examples and then see if we can generalize. Okay? For example, is 3 equal to 3?
Yes.
Yes, of course. So 3 is equal to 3. 17 equal to 17? 28 equal to 28? Do you think, are you convinced that every real number A is equal to itself? Is that right? You say, of course. You know, what's the big deal? Why make such a fuss about that? And let me write this down for every real number. All right, in this case, A. All right. What do we want to say? A is equal to A. All right. And as a matter of fact, this is a very subtle property and has a special name. It looks very simple on the surface, but later on I think you'll see that it's going to be a little bit subtle. And it has a special name, and it is called the reflexive property. R-E-F-L-E-X-I-V-E. All right? The reflexive property. For every real number A is equal to A. Let's look at another property. For example, if 2 plus 3 is 5 equal to 2 plus 3? What do you think about that one? Do you have a good feeling that, of course, that's true, right? How about, you know, is 3 plus 8 is 11? Is 11 equal to 3 plus 8? What do you think? Yes. If A is equal to B, what conclusion can you say about that? If A is equal to B, Barb says, B is equal to A. All right? Now, are you convinced that this is true for every real number A and B? What do you think, Todd?
Yeah.
For all real numbers A and B? For every real number A and B, all right? A, if, what do we want to say? If A is equal to B, then what? B is equal to A. All right? And as a matter of fact, this property has a special name, and it is called the S-Y-M-M-E-T-R-I-C, the symmetric property of equality. Okay? For every real number A and B, if A is B, then B is A. And everybody says, of course, I understand that. I accept that. I accept it. All right? And that's what we mean by a property. Okay? Now, let's see if we can think of another property of equality that you have been using a long time and you accept, you're familiar with it, and I think you do accept it. For example, if 2 plus 3 is 5, and 5 equals 4 plus 1, what conclusion can we come to about 2 plus 3 and 4 plus 1? Chuck?
They're equal.
They're equal, all right? Now, are you convinced that for every real number A, B, and C, if A is equal to B, and if B is equal to C, then A is equal to C? Does that make sense to everybody? Would you all accept that? You have a good feeling for that and say, of course, I know that it is true. All right, so for every A, B, and C, all right, what do we want to say here? If A is equal to B and B is equal to C, then what? A is equal to C. And as a matter of fact, this property has a special name, and one that we will be using perhaps even more so than the other two, and it is called the transitive property. Transitive property, T-R-A-N-S-I-T-I-V-E. Transitive property for equality. Okay? Good. Well, we'll be using these words over and over again, and even though they look like new and different words to you, I think that as you use them, you'll become familiar with them. Okay? Let's now turn to another idea, and some more properties of our real numbers. All right? Well, let's start out with an example. For example, suppose we take the number 3. All right, let me write it down here. 3 is a natural number. Is that right? Everyone agrees that 3 is a natural number. 4 is a natural number, right? All right? Suppose I take these two natural numbers and add them. I want to combine them in some way. And one way in which we can combine them is to add them. And my question is 3 plus 4 a natural number? All right? And we all say, of course, yes, 3 plus 4, that's a natural number. Now, what we say is that the set N is closed, C-L-O-S-E-D, closed under that operation of addition, under the operation of addition, all right? We take two elements in a set and combine them and get a third element in that set. We say that that set is closed under that operation, all right? Now, for example, suppose I now have the operation of subtraction. Is 3 minus 4 a number? That's a third number. Does it belong to the set N of natural numbers? What can you say about that, Jane? No. So our conclusion is that N is not closed, under what? Under subtraction. Let me use that symbol there. How about multiplication? If I take 3 and 4, for example, and multiply them, do I get an element in the set, Sally? Yes, all right. And so we can say that N is closed under multiplication. Let me use a little dot to indicate multiplication. What do you think about division? Is 3 divided by 4 in the set of natural numbers, Chuck? No. And I think there we would say, let me use this symbol for division, that it is not closed under division. Good. Let's look at another example. Let me put down the name of this idea, C-L-O-S-U-R-E. The closure, now let me use the word axioms here. The closure axioms for our real numbers, all right? Now here's an example over the set N of natural numbers, in which in one case, under addition and multiplication, it is closed, but then under subtraction and division, it is not closed. That set of numbers is not closed, all right? Let's look at another example. Oh, let me take a very simple little set consisting of the elements 0 and 1, okay? And you haven't done anything like this since probably the first grade, but let's make up a little addition table. And remember how you make an addition table? 0, 1, here's 0, 1. 0 plus 0 is 0, right? 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 2. Now I ask you, is this set closed under addition? Todd?
No.
No. Why?
Because when you add 1 and 1, you get 2, and that's not in the
And
set.
2 is not in the set. Very good. So we will say that this is not closed, okay? Not closed. Now let's look under the operation of multiplication. Let me use a little dot. Here's 0, 1, 0, 1. 0 times 0 is 0. 0 times 1 is still 0. 1 times 0 is 0. And 1 times 1 is 1. Now I ask you, what can we say about this set, David?
It's closed.
It is closed. And the reason it is closed is because
It doesn't still in the set.
the elements here are still in the set of 0 and 1, okay? So this one is closed, all right? Now, let's then jump to our real numbers. And here's a real number A, and here's a real number B. and if I add them, do I get a third number which is in the set of real numbers? And Steve, what do you say about that? Yes, all right. So let's write this down. Let's use our fancy notation for every A and B belonging to the set of real numbers. All right. What can we say? A plus B also belong to the set of real numbers. All right. And we say that the set of real numbers is closed under the operation of addition. Okay? Closure. How about multiplication? What can we say about our operation of multiplication? Here's a real number A and another real number B, and if I multiply those two real numbers, do I get a third real number? Ron, what do you think? Is that third number in the set of reals?
Yes.
Yes. And I think then we can say for every A and B belonging to a set of real numbers, A times B is a real number. Let me use the dot there to indicate multiplication. Okay? Very good. What I'd like to do, I think, is to come over here and make a table. Let's make a little bit of a chart or a table of some sort. And let's write down here properties of real numbers. Okay? Properties of real numbers. And what are we saying? We're saying that for all real numbers, A, and in this case, B, okay? Well, let's see. Let me try to make this chart in such a way so that we can set it up here for other cases. And we have here, what? Addition, something that holds true for addition, and something that holds true for multiplication. Okay? Multiplication, all right? And then, of course, right here, this is one of our axioms, which in this case, it is what? The axiom of closure, all right? All right? So what do we want to say about our axiom of closure here? For all real numbers, A and B, what do we want to say? Under addition, what do we want to say here? What do we want to write here? What? A plus B also is a real number, R. Is that right? Okay. And of course, over here under multiplication, what can we say? If I take a real number A and another real number B and multiply them, all right, the resulting number that we get is also a real number. All right? And that's what we mean by closure. Is that all right? This property of closure is very important to us. We want to be able to get numbers that are in the same set rather than outside of that set. All right? And we're going to be using this property over and over again. Very good. All right, let's look at another idea here. Number 4, in which, again, let's start out with a numerical example. Suppose I take the number 3 and the number 4. All right? And if I say add those two numbers, 3 plus 4, is that the same as 4 plus 3? And we say, Bob says, of course, everyone knows that. Is 11 plus 13 equal to 13 plus 11? What can we say? Jane? Yes. Is for every real number A and B, is A plus B equal to B plus A? And I think we'll all agree with that. And let me write that statement down. For every A and B belonging to the set of real numbers, A plus B is equal to B plus A. And as a matter of fact, you might remember the name of this property from your work last year in the 7th grade, where you were just over the set of, say, the positive rationals. Barb? Pardon me? Commutative. Now let's spell that word. C-O-M-M-U-T-A-T-I-V-E. All right, the commutative property. In this case, it's the commutative property for Sally, addition. Now let me just write in here the commutative axioms, all right, because I think we're going to have more than one. Here is one that holds true for addition. And since our lesson today has to do with addition and multiplication, can I ask you the question, here's a real number A and a real number B, and if I have what? A times B, everyone says that, Mary Lou says that that's equal to B times A. All right, so let's put that in there. For every A and B belonging to the set of real numbers, A times B is equal to B times A. All right? And in fact, let's come over here to our chart of the properties of the real numbers, and let's write down again that word commutative, C-O-M-M-U-T-A-T-I-V-E, the commutative property, all right, or the commutative axiom. We have one for addition, so what am I going to write in here? For all real numbers A and B, all right, what do I want to say in here? What do I want to write here? Kirby?
A plus B
A plus B is equal to B plus A. Fine. And of course, for multiplication, Bob says A times B is equal to B times A. Very good. All right. This is our commutative property for one for addition and one for multiplication. Okay? Let's then look at another property. Well, let's come back here. Before we look at another property, as a matter of fact, what I'd like to do is to emphasize an idea, one that I think that you have always accepted, but perhaps you haven't thought about too much. Suppose I take some numbers. Oh, 2 plus 3 plus 4 plus 5. There I have 4 numbers. I happen to have 4 numbers, all right? And I'd like to add them. I have indicated the addition by that plus symbol, which is something we've always done. But how many numbers can you add? When you start adding numbers, how many numbers can you add at any one time, Bart? 2. So you and I have learned from our grouping symbols. They say, well, all right, let's put those 2 together, plus, and then of course let's try to put those 2 together, and then we can add these 2. 2 plus 3 is 5, and then plus, and then 4 plus 5. That's another number. See, we're adding just 2 numbers. And now here we have 2 other numbers which we can add, which of course we say is equal to 14, and therefore we've added 2 plus 3 plus 4 plus 5. Okay? And this has this property of being able to add only 2 numbers at a time is called a binary. All right? We talk about, it's not a property, but we talk about the binary operation. Okay? The binary operation. Now, binary means what? It's a Latin root that refers to, David? 2. We have 2 numbers, 2 elements, okay? So, in this case, have we agreed or have we decided that addition is a binary operation? Okay? Is that right? Is addition a binary operation? Wrong. What do you think? Yes? And what are some of our other binary operations? Let me just indicate that by this plus sign. Give me another binary operation, right? Multiplication. If I have 2 numbers, I can multiply them. I need 2 numbers to multiply. By the way, the 2 numbers, one of them can be itself. That is, I can take A and multiply it by itself. Sally says subtraction is a binary operation. That's right. And of course, Bob says division is a binary operation. Even though we're not going to get into it now, I think you might begin to suspect that all operations are binary. But as a matter of fact, we have already been raising to a power, haven't we? You know, suppose I take a number A, all right, and then I may raise that to some power, let's say to the 17th power. Now, how many elements do I need in order to raise to a 17th power? How many numbers do I need in order to do that? In that case, what? You just give me a number. Can I raise it to the 17th power? How many numbers have you given me, Chuck?
1.
Just 1, all right? So the raising to a power is what we call a unary operation. And what would unary mean? That's a root for, Barb? For just 1. All right. But we are concerned with binary operations. All right? Now, with that understanding, let's look at an example. Let me take, say 2 plus. Let me just take 3 of these. 3 plus 4. Now, notice as soon as I write 3 numbers down, I'm forced into the grouping symbol because we can only add 2 at a time. And suppose I also wrote what? 2 plus 3 plus 4. And I have regrouped our symbols so that here we are adding the last 2 and here we are adding the first 2. And what relation can you put between these 2? Check.
Equal.
They're equal. Right, they're equal. All right. Well, let's make sure. This is what? 2 plus 7. And here we have what? Here we have what? 5 plus 4. And sure enough, those numbers we suspect are equal because this is equal to 9. And this number is equal to 9. And I think we will agree that 2 plus 3 plus 4 equals 2 plus 3 plus 4. Again, let's make the big jump. Do you think this is true for all real numbers? A, B, and C, Sally? Oh, you've heard of this one before. What's the name of that? The associative. A-S-S-O-C-I-A-T-I-V-E. The associative, again, let me use the word axiom. And here, in this example, this is an example of the associative axiom for what? For addition. And I think, let's see now, for every A, B, and C belong to the set of real numbers, A plus, parentheses, B plus C is the same as A plus B plus C. Is that right? Okay. Can we say the same thing for multiplication? For all real numbers A, B, and C, is A times B times C equal to A times B times C? You all agree with that? All right, you all feel that. And you say, of course, yes, it's got to be true. Let's write it down. For every A, B, and C belong to a set of real numbers, A times B times C is equal to A times B times C, all right? Now, these are our associative properties, one for addition and one for multiplication. How about subtraction? Do you think subtraction is associative? Is A minus B minus C equal to A minus B minus C? And we might be a little hard-pressed right now to prove it, but perhaps we could even take a numerical example. Barb, what do you think? It's not true. It's not associative. Is everyone convinced of that? See, if we say for all real numbers, and if I find one case for which it's not true, what's your conclusion? Therefore, it must be false. Okay? Shall we write down an example? Well, let's just take, let's see, can we take the numbers that are here? Let's try to take these numbers, all right? Let's just put it down here. There's 2 minus parentheses 3 minus 4 is equal to question mark. Let me put a little question mark over that. 2 minus 3 minus 4. This is what? 2 minus, now what's 3 minus 4? We're getting into some of our properties of negative numbers here, Todd.
Negative 1.
-1. All right, and I think I'm going to have a little trouble here, but let's see what happens. Is equal to 2 minus 3 is, of course, -1 minus 4. Now, I don't know if you yet know what 2 minus a -1 is. Brenda says 3. Is that right? 3 is equal to question mark, and here's -1 minus 4, and Brenda says -5, and 3, of course, is not equal to -5, and hence we have shown that the subtraction is not associative, right? Well, let's come over here to our chart, all right? And let's write down ASSOCIATIVE. The associative axiom, all right, for addition says what? A plus, parentheses, B plus C is equal to A plus B plus C. And for multiplication says what? A times B times C is equal to A times B times C. Very good. Now, that's really about all of the ideas that we have for today. What I would like to emphasize in looking at what we have here on the board, what we really have done is to come up with these properties of the real numbers. Notice there are really 6 properties that are given in this table. We have 2 for the closure property, right? We have 2 commutative properties and 2 associative properties. That's a total of 6 here. And as a matter of fact, if we come over here and look at our properties of equality, right, we have 3 properties of equality. And as we go through this chapter, we're going to build up these properties. We're going to look at some more properties and more, and we might end up with about a dozen of these so-called properties of the real numbers. All right? Yes, Sally?
What's the second property of equality?
That's the word symmetric. S-Y-M-M-E-T-R-I-C. And you'll have to forgive my writing. Good. Now, what I'd like to do is to look at the oral exercises, but before we do so, I would like to look over here on page 52. All right? Let's turn over to page 52, and there's a discussion that has to do with these last set of exercises. It says, in each exercise, an operation star is defined over the set of natural numbers. All right? In other words, it's not addition, it's not subtraction, it's not multiplication, it's not division. They're just inventing some operation, and they're calling it star. All right? Now they say, in each case, part A, find, this is, find 2 star 5. Now, I don't know what star is. You don't know what star is. We have to, it has to be defined for us. So they have to tell us what we mean by star. So, for example, in problem 17, all right, they define star to mean, A star B means A plus B plus 1. Okay? So, for example, 2 star 5 will be, whatever I have here for A, that's 2. All right, 2 plus, parentheses, 5 plus 1. And of course, this is what? 2 plus 6, which is 8. So 2 star 5 is 8. Okay? That's the first idea. Part B says, determine whether or not the set of natural numbers is closed under star. I take any two natural numbers here and star them. Notice what I've said. I'm not adding them, I'm starring them. All right? Will I end up with a natural number? What do you think? What's your conclusion? And again, you can't check them all because, of course, the set of natural numbers is infinite. But the question is, do you think that, or you feel that that would be a closed operation under the way in which we've defined it here? What do you think? In that example, Chip says, yes, he thinks so. Good. I think so, too. In part C, then, it says, state whether star is commutative. Well, remember now, commutativity says, for example, if we have 5 star 2, let's decide what that is. This is 5 plus 3 plus 1. And of course, 3 plus 1 is what? Am I doing this right? Oh, I wanted an element 2 instead of 3. Sorry. What? 2 plus 1 is 3. 5 plus 3 is 8. So in this example, is 2 star 5 equal to 5 star 2? And you say, yes. What do you suspect about all natural numbers in here? About this operation of what can we say about commutativity? Does anybody have any feeling for that? Chip, what would you think?
For all, are you asking for all the?
For natural numbers, for all the natural numbers, what do you think? You think that this operation is commutative? You think it will be true that 2 star or A star B is equal to B star A for all natural numbers? What do you think? What's your feeling about that? All right, I think so too. And then, of course, in part 2 of C, it says, how about associativity? In this particular example, in problem 17, do you think that star is associative? That is, do you think that A star, B star C is equal to question mark, A star B star C? What's your intuition tell you? What do you feel about that, Sally? Yes, I think so too. So as a matter of fact, I've already done. We've just done problem 17, and then I'll, if I ask you to do the odds, which I will, I'll ask you, you can then do number 19 yourself, okay? Now, before I give you the assignment, let's come back here on page 49 and look at one or two of the oral exercises, all right? It says, follow the directions given on the preceding page, and on page 49 at the bottom, it says, in exercise 1 through 10, which of the sets are closed under the operation's name, and then what? Example 1, they say there's a set 0, 2, 4, 6, ... under addition, and the question is it closed? If I take any two elements in that set, do I get another element which is in the set, which is still in the set? Sally? Yes. And it is closed because if I add any two even whole numbers, I get an even whole number. Look at example 2. Finite set, 0, 1/2, 1, under the operation of multiplication. All right, so you say, well, let's see now. If I take a half and multiply it by itself, notice we can multiply elements by themselves, right? By itself. A half times a half is a fourth, and a fourth is not in the set, so our conclusion is what? It is not closed. Okay? On the next page, 50, number 1. Just tell me whether it is closed or not closed. Ron?
It's not closed because 3 plus 3 is 6.
Good. That's outside the set. Let's just do some of the odd ones. 3, the whole numbers. What can you say about that? Chuck?
It's closed.
It's closed under multiplication. Number 5, a half, 1, and 2 under division. Jane? Not closed.
And a fourth is not. Oh.
Well, it's under division,
Yeah.
but
So 1/2 does be closed.
it's closed. Jane says it's closed. Can anyone find a number in there which might go outside the set? Chip? 2 divided by a half is what? 4, and 4 is outside the set, so indeed it is not closed, all right? 7, 0, 2, 4, 6 under subtraction. Brenda? Not closed, because you end up with a negative number, perhaps. 9, the powers of 3 under multiplication. What can you say about that? Steve?
It's closed.
It's closed, all right? Powers of 3, that means what? 3, and then the next power of 3 is 9, and the next power is 27, And if I take any one of those powers of 3 and multiply it by any other, and take any other power of 3, do I still have a power of 3? And I think the answer is yes. That's a good question. The next batch says, name the property of real numbers or of equality illustrated by each of the following true statements. So number 11, what property are you using there, Barb? For or of addition. Let's just jump around. 15, what can we say about 15? Number 15 there, Chip? Associative property multiplication. Good. Let's look at 19. If x denotes a real number, that is x belongs to R, and x plus 3 is equal to 0, then 0 is equal to x plus 3. One of these properties here, Kirby? No, it's not a commutative property. It has something to do with equality, I believe. Ken?
Symmetric.
The symmetric property. Very good. It's the symmetric property that we have here under number 2, properties of equality, the symmetric property. All right, let's jump down to, such as 21. For all real numbers a and b, a half times quantity a plus b equals quantity a plus b times a half. Be careful. They're trying to confuse you a little bit there. Who has, Ken?
Commutative.
The commutative property. Very good. Very good. You see, we just switched things around. We haven't regrouped anything there. In problem 23 now, the directions change. It says, name the property that justifies each lettered step in these chains of equalities. A check mark shows that the step is justified by the substitution principle. Remember the substitution principle we had earlier. In writing each chain, the transitive property of equality is also used. So in number 23, the left-hand side equals the right-hand side. What have they done from the left to get to the right side? What is the change and what's the reason for that, Ron?
Commutative.
The commutative property for addition. And then the next line down, what then can we say there, David?
Associative.
The associative property. And then the next step, they put in the check mark, which means that they have used the substitution principle for what? 39 plus 101 is the name for 140. And so on. Let's jump over here to number 27. X plus 1 plus y plus 4 is equal to all of that. Now, what is the property for the first line? In the first line under A. Brenda, what do you think? The associative property for addition. The next line. The elements appear in the same order, but the parentheses, the grouping symbols are changed. Sally says associative. The next line, 1 plus 4 is 5, and they put in the check mark to indicate the substitution principle. So now the next line. Mary Lou? The commutative property for addition. Finally, the next line, the last line there, 5 plus parentheses x plus y. Chip says associative property. Very good. All right, let's turn to our homework assignment, and that's our lesson for today. This is assignment